In this lecture on basic logic, we'll be covering validity and introducing the concept of conditional statements. As I've explained previously, validity is the quality of the form of an argument, such that if the premises are true, the conclusion must also be true. This quality of form can be demonstrated using argument forms that we will eventually use as inference rules in natural deduction. An example from our text: P or Q. Adam loves Bertha or Adam loves Eve. Not P. Adam does not love Bertha. Therefore, Q. Adam loves Eve. To demonstrate the validity of an argument using a truth table, first lay out every possible combination of truth and falsity of the atomic statements as a reference in the first two columns of the truth table. Then separate the atomic statements from the premises of the argument with an empty column. Then, enter the truth table definitions of each premise and add another empty column to the right. In the last column, enter the truth table definition of the conclusion. With the truth table now complete, we can test the argument for validity. To do so, we need to make sure that in any case where the premises are true, the conclusion is also true. Any case where the premises are all true is called a critical case. So, any case with a false premise can be ignored. As you can see, there is only one critical case, and since the conclusion is also true, we know this is a valid argument. For contrast, consider the truth table for this invalid argument. If you look at the second critical case, you'll see that the premises are all true, but the conclusion is false. We can reason our way naturally to this revelation as well. We know that the disjunction is true, and that the first disjunct is true, but the disjunction can be true with only one disjunct. Therefore, it doesn't follow from the truth of the first disjunct that the second is guaranteed true as well. An argument is sound when it is valid and has all true premises. So, the formula for soundness can be expressed as validity plus true premises equals soundness. Teller uses this example. P or Q. Teller is 10 feet tall, or he has never taught logic. Not P. Teller is not 10 feet tall. Therefore Q. Teller has never taught logic. The conditional operator says that if the first atomic statement is true, then the second atomic statement is true. The first atomic statement is called the antecedent, and the second is called the consequent. It is called the conditional statement because the consequent is true on the condition that the antecedent is true. So, we have another truth table definition to memorize. This section continues with some theoretical concerns about the nature of the conditional and how it fits into the greater logical system. Though these concerns are inappropriate for a basic logic course, I'll address them in another way than Teller does so that you can become comfortable with the system and its reliability. First of all, the system does work reliably. And second, cases where the antecedent and the consequent of a conditional statement do not have the relevant relationship that they would need for one to result from the other are actually quite noticeable. Furthermore, if we reframe the way we analyze the conditional truth table, it can make a lot more sense. Consider this treatment of the conditional that I first read in another popular logic book called A Concise Introduction to Logic by Hurley. An example is given in some edition that goes roughly like this. Look at the truth table while imagining this scenario. I, as your professor, tell you that if you get an A on the final, P, then you will get an A in the class, Q. Now, in which of the truth table cases would you call me a liar? In the first case, P is true, you got an A on the final, and Q is true, you got an A in the class. The conditional statement, if P then Q, is obviously true, and you would not call me a liar. In the second case, P is true, but Q is false. You did not get an A despite getting an A on the final. In this case, if P then Q was false, and you would definitely call me a liar. Now, Let's look at the other cases that give us trouble in the teller text. 3 and 4. If P is false, you did not get an A on the final, but Q is true, you did get an A in the class. You would not call me a liar because you could have gotten 100% on everything else and maybe even did some extra credit and gotten an A that way. It is still true that if you had gotten an A on the final, you would have gotten an A in the class. Now, in case 4, P is false, you did not get an A on the final, and Q is false, you did not get an A in the class. You would not call me a liar in this situation, and it is still true that if you had gotten an A on the final, then you would have gotten an A in the class. That explanation should suffice, but Teller also very clearly explains a systematic reason for the conditional truth table definition. Reason through this with me before we get technical. If I say that if P is true, then Q is true, that's the same thing as saying it's not the case that P could be true while Q is not true. For example, if it rained last night, then the grass is wet is the same thing as saying it can't be the case that it rained last night and the grass is not wet. Now let's look at the truth tables for these. With what I've added from Hurley, and the fact that the truth tables align with our reasoning, our concerns about the conditional should be resolved. These concerns and the meta-logic discussed before are concerns for people who have already learned and thoroughly come to understand the power and value of logic. When you're writing your dissertation on logic for your PhD is when you should address these kinds of problems, if they even are problems for the use of logic at all. The takeaway from all this should be that we, as philosophers, need to put logic first in our arguments and expositions to neutralize the problems that arise from how vague ordinary language is. Which brings us to the biconditional. Since the biconditional is mostly reserved for legalese, that is, rarely used in ordinary language, I'll only cover the truth table. We won't have much use for the biconditional in critical thinking and writing. The biconditional. P if and only if Q is logically equivalent to if P then Q and if Q then P. The biconditional can be understood any way any other bi term can be understood. It just means it goes both ways. Next time, we'll finally get into the good stuff, introducing the idea of natural deduction.